exactly what it says there. And let's see the timing. I've got to give this talk again tomorrow, and I usually waffle on, you know, and go over and stuff. And I've been told today I should only speak for 40 minutes. So this is after I prepared the talk, so that's a bit hard. I'll try and do that. Okay, so a vital clue to determining how planets form is to find evidence for the absence or presence of planetary cores. And such evidence might come in the form of a steep density profile. And the usual way to measure density profiles of objects is to try and measure their absidal motion constants. But of course, a body needs to have a companion in an eccentric orbit in order to do that, and the usual thing to do is to measure the rate of absidal advance. So you've got to measure the change in something. So today I want to tell you the story about how some simple dynamical systems analysis, which I did a couple of years ago when I was studying, I still am, short period planets with companions, has been used to determine the absidal motion constant, or what planet people call the love number, of the planet in a new system, recently discovered system with quite a massive companion. And in particular, one doesn't need to actually measure the absidal motion. You can just, you don't have to wait for the system to move, in other words. You can measure it directly using this so-called fixed point theory. And then after I tell you about that, I'll spoil the story a little bit by pointing out that this system that these guys have used this fixed point theory for almost certainly isn't coplanar. And the theory I developed is for coplanar systems, so that sort of mucks up the beautiful result, potentially mucks it up anyway. And after that I'll, as advertised, tell you the whole story leads on to a discussion of retrograde planetary orbits and how nature might produce such amazing structures. So just to remind you, a little quick tutorial on binary stars and absidal motion. If Pomega, there is the argument, or the longitude of the ascending, the longitude of the absidal line. One tries to measure the change in the orientation of the orbit in the orbital plane. So this is absidal motion, not precession. It's often called absidal precession, but precession is actually the rotation of the plane, right? And absidal motion is rotation in the plane. And this, for binary stars, usually has three components. One from the spin bulge of the stars. So you'd have three more. You'd have these three terms here. Is there a pointer or a stick? Something. Here's a stick. So the absidal motion comes from a term from the quadrupole moment from the spin bulge, and a term from the tidal bulge, tidal bulges if both stars are contributing, and the relativistic or post-Newtonian potential of one or both stars. And here are the expressions for these three contributions, and if you have a double line eclipse in binary, you can pin down all these parameters and actually deduce these absidal motion, the absidal motion constant. As I said, this is called the love number. Actually, the love number is twice the absidal motion constant for historical reasons. And one of the key things is that the more centrally condensed the object is, the lower the absidal motion constant. So that's theory 100 years old. And here's a couple of interesting examples too. The first one's a massive binary, and the absidal motion for this system is measured at it's reasonably large per year. The smaller the eccentricity, the more difficult this is to do. But the thing to notice here is that by far the biggest contribution to the apsidal motion for this system is from the tidal bulge, the bulges of both these stars. Here's a pair of, 10 times less, and the apsidal motion is smaller. The eccentricity is bigger, and actually I haven't shown the error, but it's easier to measure this one than the other one, I think. And again, most of the contribution comes from the tidal bulges, but a significant contribution comes from the relativistic potential of the stars. But as I said, this involves, this way of measuring or estimating the apsidal motion constant involves measuring, waiting for the thing to move, to rotate, for the orbit to rotate. As far as I know, this hasn't been done for planets, and I can't imagine how it could be at the moment, as far as measuring apsidal motion is concerned. Now, this system, HAT P13, is what I'll focus on today mostly. This was discovered this year, or at least announced this year, a few months ago, and it's the first system to have a companion that's close enough and massive enough to do what I'm going to tell you about today, to actually induce a non-zero eccentricity in the inner planet that should be, with this period, be actually circular. Would be circular if the companion wasn't there. This is a theoretical apsidal motion, and there's no hope in hell of ever measuring that, or not at the moment anyway, because the error on this apsidal angle is huge, much bigger than the change per year. Again, the tidal bulge, this is really important for the story later on. The tidal bulge contributes half of the apsidal motion, and the relativistic potential of the star contributes quite a lot too. And this one here, Omega.c, is the contribution to the apsidal motion of the inner planet from the outer one. I'll say more about this system later, and I haven't even told you that the outer planet actually has a period of over a year. But one of the important things here is that circularisation, well, it depends on the Q value, but the circularisation timescale for this short period planet is probably shorter than the age of the system. So we say the second planet is...
That 0.02 eccentricity is approved in the orbit?
Yeah, I'll show you the data on this later, or I just, for now, just wanted to point out what kind of apsidal motion such a system would have if you could measure it. And I'm saying you can't measure it, but also I want to point out all these different contributions. So the star, for example, doesn't contribute much at all to the apsidal motion, nor does the spin bulge of the planet. So the theory of tidal evolution, just to quickly remind you or tell you, the minimum energy state of a binary system, or maybe two stars or a star and a planet, is a circular orbit with synchronous rotation. So both the bodies are rotating synchronously with the orbit. And the spin axes should be aligned with the orbit. And one might define a short period system as being one where the circularisation timescale is less than the age of the system, but since we don't really know what these time scales are, it's perhaps not a very useful definition. Nonetheless, many short period planets have non-zero eccentricities, and I don't know, it seems, talking to people in the last couple of days, it seems that maybe one shouldn't expect them to be zero, because perhaps the Q values are much bigger than we think. I don't know, it's all very confusing, but let's just assume for the sake of this story that the system I'm going to tell you about today would be circular if it didn't have a companion planet. But many of these things with non-zero eccentricities have anomalously large radii as well, and that's a typical kind of radius of these hot Jupiters that have non-zero eccentricities. So back in 2001, we suggested that these systems actually have unseen or undetected companion planets, and these companion planets were pumping up or inducing eccentricity in the short period planet. So 2007 I put together this theory I mentioned before for a tidal evolution of short period planets with companions. And a key to the story is that that theory is coplanar, but that hasn't stopped people using it. And I had in mind in particular to understand something about these inflated planets. But these chaps, actually someone called Darren Ragozine, perhaps not pronouncing his name properly, but realised that he could use this theory, that one could use this theory to actually infer something about the structure of a short period planet. But these chaps, as soon as this HAT-P13 system was announced, they were very quick off the mark to apply this theory and for the first time say something about the love number of the short period planet. And as I said before, one can do that. I'll show you how you do this without actually measuring epicidal motion. So here's just very sort of brief overview of how the fixed point theory works. So you have two planets. The innermost planet is close enough to the star to experience tidal evolution, tidal damping, and without the second planet, the eccentricity would just decay to zero. But there's a continual forcing from the second planet, and the two parameters that are important here in this coplanar theory, the two variables are the eccentricity of the inner planet and the angle between the epicidal lines. So, and so here's the rate of change of this thing I'll call eta, and we see this is a second order, non-linear, autonomous system of ordinary differential equations. And one can look for the fixed points of such a system, and that's exactly what I did. It's a damped system, so it should evolve towards such a fixed point. And just to point out that the information about the structure of the planets, amongst other stuff, lives in this thing here. These various constants are functions of mass ratios and the ratio of the semi-major axes. So you put these two things equations equal to zero, and you find the fixed points. You find that eta evolves to either an angle very close to zero or very close to pi. I've just done the zero one here. And the angle is related to the Q value of the planet. So for sensible values of Q, this is very close to zero. On the other hand, the eccentricity evolves to a non-zero value. This is the fixed point eccentricity. It's got a very simple form. It involves the ratio of the semi-major axes, the outer eccentricity, the ratio of the two masses of the two planets, and this thing gamma, which contains all the information about the structure of the planet and the star, the innermost planet and the star, as well as relativistic potential. So these gammas are actually the ratio of the rate of epicidal advance, or the contribution from whatever, to the epicidal advance due to the second planet. So they're dimensionless things. But anyway, the main thing is that all these things can be measured, and you can infer. You can infer gamma. So that if you can measure this accurately, as I said, you don't have to wait for the system to rotate in its plane. You just need to be able to measure this accurately. Of course, these other things as well, but this particular system is a transiting system, and they also have radial velocity data. They have a lot of quite accurate measurements. So that's the idea. Measure this and know something about the structure of the short period planet. Infer. And well, again, I just point out that these are the two biggest contributions. These are measly compared to these two. We know exactly what this is. And well, as far as we know the mass of the star, and so we just can figure out what gamma B is. It's kind of fun to look at how these things, if you're into dynamical systems, how this works. So these are direct numerical integrations, and here I've plotted the eccentricity of the short period planet against this eta, this angle between the absidal lines. So it's kind of a phase space plot. I've chosen a relative, pretty small Q value just to speed it up and make it clear what's going on. Start the eccentricity at 0.1. This thing circulates until it hits this, comes close to the fixed point. It librates and evolves towards this point here. Here's the eccentricity as a function of time. You can see circulating, libration and evolution towards the fixed point. I showed that this happens on a timescale. Well, this phase happens on a timescale of 1 circularisation timescale, and it finds the fixed point after 3 circularisation timescales. So for realistic Qs, this just, although each of these oscillations is correct as far as the time, the secular oscillation period is concerned, it would take a lot longer to reach these points with a realistic Q. I assumed to derive that fixed point formula that the outer eccentricity remains constant, but actually it evolves slowly over time on a timescale much longer than the age of the system. And I worked out the timescales on which on which the system actually evolves to the doubly circular state. So it's kind of nice. You don't need tides in the outer planet for it to actually circularise, but it happens on a very long timescale. So you can do this if you have a system where in general, where the outer planet's mass is relatively large, and that's true in the case of this HAP P13 system. You don't want the outer planet to be too far away, and it really helps if you have a decent eccentricity. And this system fits the bill. The mass ratio, the outer body is, well, it probably doesn't even deserve the name planet if you take 13 Jupiter masses as your boundary. Its minimum mass is 15 Jupiter masses, the outer thing. The inner one's about 0.8. The eccentricity of the outer planet's 0.7, and the ratio of semi-major axis is 0.03. So the outer guys are about in one and a bit AU away. Well, you can't, I don't expect you to look at all this, but just to see the accuracy with which they have pinned these various things down. Of course, the period's always very accurate in these things. It's a transit. It was discovered in transit with the HAT-NET project. They did Keck follow-up spectroscopy, and then it's actually been observed with Kepler. So they have a lot of good data for it, and they're going to observe it again next month with Spitzer and pin down the eccentricity a lot better. So the eccentricity is at the moment estimated about 0.02, but this is the thing that contains all the vital information. And as I said, it's the outer one is, 1.2 AU away. It's period's a bit over a year. And what else is interesting here? Yes, it appears to be one of these inflated planets with a radius about 1.3 Jupiter radii. Okay, so the thing is, the guys particularly want to be able to, these guys, Badigan, Bodenheimer and Laughlin want to be able to say something about whether this planet has a core or not. So the way they go about that is they make a grid of models. They vary the core mass and what they call the tidal luminosity, the amount of rate at which energy is deposited into the planet. This is really Peter Bodenheimer's bread and butter to make structural models of planets. And then they can pick out which of those models matches the observed mass of the planet and the observed radius. And from that, they can calculate the love number, tidal motion constant, and the Q value. And using that formula, the fixed point formula, they can work out what the eccentricity should be. So they're going to treat this as an inverse problem. But just have a look at the data for all the Q value aficionados here. It's a bit funny. These, let's see what they've done. They've done a series of models. This is no core, 40 Earth mass core, and so on. These three values of the radius of the planet. This is the best fit radius, and this is plus or minus 1 sigma. And they do this procedure, and they get these love numbers. And actually, an n equals 1 polytrope has a love number of about this 0.3 something. And but look at the Q values are really small for all these models. So given what my colleagues here tell me, they all look a bit small. Maybe this one's okay, but that's a coreless model with the smallest radius. I don't know. It's a bit, something's missing. But the eccentricities they calculate, well, they're something like what are observed. So it'll be really interesting to see what the follow-up observations come up with this eccentricity. But perhaps the reason they're out is for this reason. A system with such a high outer eccentricity, I think it is almost certainly not coplanar. And that fixed point theory is for coplanar systems, as I said. So I'm first of all going to show you some a couple of models of the possible origin of this system, which assuming, sure nature may have many ways to produce a thing like this, but anyway, I'm going to assume that there once was a third planet that scattered off the outermost planet, the one we see today, and left the system in the state we find it now. So what have I got here? Here are the three, so I start the eccentricities of these three planets. So this is EB, the one we see, the innermost planet, the middle planet, and the hypothetical outer one, all around 0.1. Well, the outer one I start at 0.17. And they're all a bit out of the plane, about 10 degrees out of the plane, and sort of arbitrary longitudes. And I start the middle planet at 1.5 AU. It's now a bit 1.1, and the outermost thing at 2.9 AU. And I give the outer thing the outer thing's quite massive because I need it to scatter the outer one we see today into a high eccentric orbit. And the one we see today is at least 15 Jupiters, so you need a hefty thing. The authors of the discovery, the people who discovered this system, hypothesised that the outer thing got its eccentricity by scattering off the inner one, but I think that's impossible. The inner one's not massive enough. Anyway, so the thing goes along. This is real time. I involve an unrealistic Q to see how the damping works, but otherwise this is real. Real time scale. It's clear that this system's unstable from the start, and eventually they come close enough for quite a lot of angular momentum to be exchanged between these two. In fact, the minimum they don't really have a close encounter. The outer planet comes within 10 times the inner semi-major axis, and they fiddle around. Eventually, the outer planet's chucked out of the system. these are eccentricities, so those eccentricities above 1. And here's a blow-up of this innermost planet and its tidal evolution and its evolution towards this fixed point. It's not quite fixed actually, we'll see it, but we expect to see this kind of oscillation when it's not in the same plane. Also going on at the same time is the inner semi-major axis is shrinking due to tidal friction. The radius of the inner planet is expanding due to tidal heating, and well, the middle planet, when the outer planet scatters out of the system, it's got to get its energy to do that from somewhere, and it swipes it from the middle planet. So we end up with a system not unlike what we see today. Of great interest is how the relative inclinations evolve, and especially the stellar obliquity. I'm going to say quite a bit about that. But here we are. Here are inclinations relative to the original invariable plane. So you've got 3 planets. The angular momentum is dominated by the outermost planet, and they fiddle around a little bit, around 10 degrees each, and then eventually the outer one's scattered out, leaving C behind to dominate the angular momentum, and B, well, try and explain what these oscillations are in a sec. Here are the inclinations of the orbits relative to the new invariable plane. So take the outer planet out of the system, and we see that this is the innermost planet B, and it settles down to an inclination of about 10 degrees. Now the stellar obliquity, this has been big in the news. One can measure this, or at least the sky projected value of this, using something called the Rossiter-McLaughlin effect. And it's the thing that tells us these 2 systems I'll talk about soon are in retrograde orbits. But just for now, it's the angle between the spin axis of the star and the orbit normal to the innermost planet. The orbit normal of the innermost planet. It slowly creeps up during this period here, and then after the scatter, it's left in this oscillating kind of state. And this is going to be almost certainly true for every system that they observe, even if there's not been any scatter, there'll be this kind of oscillation. Oh, well, if there's a companion planet. What's going on with this is, so here's the original invariable plane, and I've put the star's spin axis in the same direction as the normal to the original invariable plane. The star doesn't care about all this scattering and stuff going on. The torque on it is almost nothing. So it will stay in this direction while everybody else does whatever they do. So the outer planet gets scattered out, leaves the system, and we have a new invariable plane governed by this outer planet. So the normal to the new invariable plane is more or less in the same direction as the normal to this outer planet's orbit. In the meantime, we have the star now oblique to this normal, and actually this diagram I made in my paper doesn't refer to this. This is quite a mild scatter. I'll show you another example in a minute where it scatters the scatter angle's big. But the point is that the little orbit really gets bullied around by these other guys with big angular momentum. Its orbit normal precesses around the invariable plane normal, and so sometimes the angle between it and the star is relatively small, and sometimes it's much bigger, and that's what this oscillation is. And so they are going to try and measure this stellar obliquity for this special system next month as well. Now, this is kind of fun. I was just mucking around with this code. I have have 3 planets and spin orbit coupling and tides and GR and blah blah blah. I change the outer eccentricity by 10 to the minus 5. So this is the butterfly effect at work. This is a chaotic system. This time, well, again, the outer planet gets chucked out, actually with a higher eccentricity this time. But the amazing thing is that the stellar obliquity is right up at 70 degrees. The radius of the planet goes right up to 1.7, more past 1.7 Jupiter radii. And actually, one of these retrograde systems, this is not retrograde, but it's getting up there. One of the systems has an enormous radius like this. Again, the middle planet shrinks down to something like what we see. But the main point is, well, and here's the final eccentricity. It's not a fixed point, it's jumping around and it'll keep doing that. What else can I say? Semi-major axis shrinks. And yes, the mutual inclination of the 2 orbits after the outer body scattered out is about 70 degrees, which is the average of this here. Okay, just to quickly compare, so this is model 1, model 2, everything's identical except this initial outer eccentricity. One produces a relatively small obliquity, one produces an enormous obliquity, and it could well have, if the scatter had been a little bit closer, it could have tipped it over into a retrograde orbit. And so my, hypothesis for what we're seeing with these retrograde planets is that this is what's happened, some earlier scatter. And the radius of the innermost planet is very different in both cases, just from that tiny different initial condition. So if we include mutual inclination in this dynamical systems theory, we end up replacing a fixed point with a limit cycle. And so this is a plot similar to what I showed you before for the coplanar example, but this is not nearly as smooth. Here's the limit cycle squashed. Here is, let's see, yes, this is an enlargement of this little patch here. So this is a phase space again, if you like to call it that, the eccentricity of the inner planet against the angle between the absidal lines. The red curve is the numerical solution that fiddles around and eventually settles onto this limit cycle. Here we see it here in eccentricity against time, and it just becomes nice and regular and stays like that. And the blue curve is the theoretical limit cycle, which comes from a generalisation of the theory I showed you before. So the main thing here is how this affects one's ability to say something about the structure of the planet, and unfortunately it really screws it up unless the inclinations are small. So what have I got here? This is a series of models. We've got the inner eccentricity versus time. Again, I've used an extreme Q value to get it to do what I want it to settle down. You can show that it doesn't, it will settle down to effectively the same, almost the same value if you have realistic Q values. Anyway, these are relaxed, almost relaxed systems. I start them at their theoretical sort of fixed point values, and so they're all already almost relaxed when I start integrating. The red lines are the theoretical averages, and the black lines are numerical. So for for coplanar system, of course, it just goes to a fixed point. And then when you increase the mutual inclination, you start to get this oscillation. But so 2 things to notice. The average value, well, here is the formula for the average value coming from that modified system. And it's identical except for these inclination functions that appear here. I haven't bothered to write them down. They're just simple trig functions, trig expressions, which reduce to 1 when the inclination is 0. But the average value of the eccentricity reduces as you increase the inclination. So that's the first thing to notice. If this system that they're observing actually has a non-zero mutual inclination, if it's small, the wiggle isn't very big and you can still pretty much say something about the love number of the planet. But when the oscillation increases, when the inclination increases and the oscillation amplitude increases, it really screws it up. So sorry boys, if it's measured to be substantial, they won't be able to do what they hope to do. If you want to see what the DEs look like, I would want to see what the DEs look like. This is just out of the paper. This is what it looks like without inclination, and then there are extra terms. They're just forcing terms, and the forcing period is 2 times the excital motion period. But you can read the paper to see that, but it's kind of neat how you have these limit cycles coming out. So what I've plotted here is the average eccentricity, that's this middle line here, as a function of mutual inclination. So we see, so this is a coplanar system, and the average just goes down and the amplitude increases. This gives the maximum minimum eccentricity. Past here the theory breaks down for well understood reasons. And also for retrograde systems you just get the mirror image of this. So the theory gives the whole range. Anyway, and how does it depend on the love number? So this is for, these curves are for this love number, and if I vary the love number, if I have a 0 love number, I get a higher eccentricity. So as long as the mutual inclination is less than 10 degrees or something, you could still pin down the love number of the planet if you get an accurate measurement of the eccentricity. But past there, you know, it just becomes, the waters become muddy. You really can't say, give a unique value for excital motion constant. For even higher inclinations, you get quasi oscillations to make it even more interesting. And in fact, because of these quasi oscillations, you can conclude that the system would rapidly evolve away from these inclinations. These pictures are very busy, and I don't expect you to really look at them too closely. This dotted line is, so I've got the maximum eccentricity you can have for a mutual inclination of whatever. The dotted line is without any structure, just point masses, and here's the famous 39 degrees. But when you have other contributions to the absidal motion, this minimum quasi angle increases or decreases if you're retrograde. But the main thing here is that if you can induce big eccentricity, then you can circularise quickly, and the inclination actually shrinks and moves the system away very rapidly to some minimum inclination. So the thing is, one can conclude, at least for this HAT P13 system, that it can't have an inclination in this range. Even for, I mean, I've got Q 10 to the 6, even if you're up at 10 to the 7, it doesn't make much difference. And, well, actually the second model I showed, the one that scattered into the high relative inclination, actually has a little quasi period. This is cut very short because I've got such a small Q value, but the system tries to do this quasi go high up to 90 degrees actually, but it quickly, the system quickly, the orbit shrinks, takes the system away from this very strong damping situation. The radius of the planet puffs up, as a result, and it gets stuck at this high radius. So that's a quasi thing. So, well, I've said that. I predict that the system will not be found to have a mutual inclination in range. Now, you might wonder, how do you measure mutual inclination? Apparently, I don't think it's ever been done with a system, but in principle, you can use transit timing variations to actually pin down or say something about the mutual inclination. So, I'm hoping they'll be able to do that for this system. I won't say fill out what I've written there, but just to say that the stellar obliquity is measured via the Rossiter-McLaughlin effect. This is one of the most beautiful things I've seen in astronomy. So let me show you. You may all be experts in this, but I don't think, I'm pretty sure that's not true. So I'm going to show you how the Rossiter-McLaughlin effect works. These are the two systems that have been discovered to have retrograde orbits. Well, actually, one of them is a bit iffy, but we will chase that one to see. I'll show you why it's iffy in a sec. Okay, well, this is from a public lecture I gave, but the Rossiter-McLaughlin effect is simply you have line broadening due to the rotation of the star, and when the planet transits, it blocks out either the red or the blue side of the line and skews the line so that you have an effective radial velocity shift. And you have a look at this beautiful, beautiful data. For the most famous transiting system, 209458, this is the famous Hubble data, and there's actually error bars on those data there. It's amazing. So Josh Wynne is the world expert on doing this, and here is, so this is a radial velocity curve for this system. And here is the system during transit, and here it is blown up here, and you can see this beautiful radial velocity anomaly, they call it, which allows one to actually, from the shape of this and the amplitude, say what the sky projected value of the stellar obliquity is. It's amazing. So we can say they've done this for well, they may have done more now, but as far as when I last looked, they've done 13. Measured this for 13 systems, and 11 of them are all consistent with the usual planet migration model in the disk and just aligned, spin and orbit aligned and so on, within 10 degrees or something. But 2 of them are definitely not. And so if you have a retrograde orbit instead of a prograde orbit, you find, well, it's just the opposite, just flipped. So you have the anomaly is upside down. You could have transiting across, I mean, with the star rotating this way, you could have the transit that way or that way. That gives a different signature. But it's this one we're interested in today, the retrograde signature, the opposite to prograde. So let's see. Data here is, this is a system that was already known, but they've observed it in transit spectroscopically, and they get the undeniable signature of a retrograde orbit. In fact, they've got reason to believe that it's just retrograde, near polar, this one. It's a puffed up planet, consistent with my little scatter model. So that's one of the systems. Now here's the other one, and there's only 3 data points in the transit, and so it's and look at the scatter in the data anyway. I mean, look at that. That's not being blamed for anything, and neither is that. But anyway, nonetheless, there it is. But the planet, the innermost planet, it's only half a Jupiter mass, and it's got a radius of 1.7. That's just happens to be the same as what I showed you before, but I mean that's really suspicious. So I'm not an observer, but I was asked to go in with Penny Sackett and Dan Bayliss on the Magellan proposal. So it's very exciting. We'll find out next month if we get time to actually observe this system in transit spectroscopically and try and get some more data on this and confirm or otherwise whether this thing really is retrograde. So that's my, oh well, we've seen that slide before. It's my last slide, just to remind you that we're talking about these, you know, possibly high obliquities being produced from scattering events, and well, there's a lot to do, but it is a bit sad that perhaps this theory, if for a mutual, non-zero mutual inclination, might screw up the possibility of determining the structure of the planets, but we'll see. Anyway, I'll leave it there. Looks like my timing's okay. Thanks. So, let me put that picture back. Wow. Any questions? Yeah, Pardon?
So, well, first of all, I already mentioned, well, in this conference.
So, say that again?
Well, I have a comment, well, which I already did during this conference in Edinburgh, that in fact, well, Kazai effect should be called Lidov Kazai effect, because it was some chap Lidov who discovered it 1 year. Well,
Who?
Lidov, some Russian.
Oh, well, okay,
who
yeah.
did it, well, actually a year.
Well, okay, send me an email with the exact spelling, and from now on I will say it. But
yeah, but it's...
No, seriously, I think it's really important to
I'll
have
give
priority.
the references.
And also, speaking of Kozai, who does get the credit, I'm not aware of anybody's fair enough discuss this, in actually inviting this famous man to anything. So he's there where, actually the Japanese, do you know Shigeru Kozai? Mr. Kozai?
No.
Is he, I mean, it's time he got more credit, I think. That's my impression. You know, we're just using Kozai all the time, you
But
know,
normally
this
it's what
guy just
people
doesn't
do
get...
well. They just pick up some well name and after that...
Oh, look, you know, I believe in giving
But
credit
anyway,
where it's
well,
anyway,
also-
that's just a side.
Yeah,
Go,
I also have a question
Yeah.
about this tidal luminosity business, because first of all, presumably it depends on position, well, in the star. Where this,
yes. Well, yes, except Peter tells me that it doesn't matter.
it doesn't matter.
No.
So, well, it doesn't matter whether you
He's tried, he puts it in the core, he puts it in the middle, he puts it near the edge, and he just gets pretty much the same result. It's hard to believe, but anyway.
And
That's,
do you know, is in principle, well, any chance, well, in future, just, well, to measure tidal luminosity, well, from some kind of observations?
oh, don't ask me, I don't know.
Transits,
Yeah, no, that's a good question, but I really don't know. Well, I certainly haven't thought about it. Yeah, I don't know. How would you do it if you've got an idea?
well, but in principle, well, just looking at...
The brightness of the thing.
Yeah,
Actually, you know,
Secondary transmission.
the second,
second
it's
the
just,
transit,
actually, yeah, it's amazing. If you've seen the
Infrared.
Kepler data, I haven't got it here, the Kepler data for one of these transiting systems, you know, and they see the phases, also, of course, the secondary transit, it's just amazing. So maybe, I don't know. That's a good question.
If you look at the data up there as it is,
Yeah.
doesn't look right. The place where there's the biggest error is right, that's right there, and next door to it is right in a very important place for the theory, and it's, you know, it's far bigger than all the rest of the errors, and that theory is not quite right.
Okay. You tell them, Donald. Well, I'll go and tell them. Josh, you're not doing it properly. Hey, but you know, oh no, but actually all the other measurements are the other way. No. You think. There's a system called DI Hercules, DI Her. Have you heard of this? This is the famous massive binary that people accused of violating GR years ago in the 80s, because the excital motion of it is much less than it should be. So, and well, you know, maybe there was a third planet, star, or whatever, but it turns, this Josh Wynne has now measured this Rossiter-McLaughlin effect for this system, and the system, they're just, the stars are just spinning on their sides, and you know, it's I guess the data for that's better. Actually, I was going to show that today, but I didn't. You didn't put it up. But anyway. Well, I'm sure they'll go after more data for this, and we'll see how it pans out. But as for the other one, I mean, Donald, if you criticise this one, the other one's really rubbish, but we'll see. I mean, you know, like, let's not look at that. Let's ignore that. Anyway, it's still beautiful.
Just a comment. It seems to me that much of the non-linearity in the equations you wrote down disappears.
The one on the eccentricity,
Yeah.
if you use complex numbers, that goes away. Well, it doesn't matter.
It might be easier to think about it.
Well, the non-linearity doesn't really make it difficult because in this case the eccentricity is small. I mean, it's easy. Well, actually, that should make it difficult, but come to think of it. But I mean, it seems to work very nicely. You know, you compare it with
But you might
numeric.
find an analytical solution.
Oh, okay. Yeah, well, there's quite a bit of analytical solution in my papers, so maybe it's there anyway. But yeah, the limit cycle stuff was a little bit trickier, but it's still pretty straightforward. Joe?
Is there anything like Cassini states in this problem where things drop down?
Yeah, well, I wondered about Cassini states because I wanted to work out a time scale for the inclination to reduce. But the Cassini state of the planet is totally pathetic. I mean, there's no, I've been talking to Dan Fabrici about this, and he's an expert in such things, and he wondered about that, but really, yeah, it's really quite pathetic. So, sadly, because it's so beautiful. No, so because I mean, I needed a dissipation term for the inclination, but I found it elsewhere. Sorry?
Most people will be surprised to hear or see that the heaviest planet on the safely on the outside was the one who's escaping. Can you enlarge?
Oh no, it wasn't the heaviest. The heaviest one was the middle. I arranged it so that the outer one was for sure going to escape, but not the middle one. Well, of course, there's no reason why you couldn't have an exchange and leave the system in this state. But that's just the way I set it up. Yeah. So, well, I mean, I don't know what it says about, I mean, they're such massive bodies. Well, the one we see is at least 15 Jupiter masses, and, you know, nature may be quite happy to make, you know, a system like that without any fancy scattering or whatever, I don't know. It's a pretty short period though, it's 1 AU, so I don't know.
Anyway, nature will sooner or later give you one with low inclination. Just wait a bit.
Oh, well, the first one was low inclination. The first model I had was low inclination, and then the next one with almost the same initial conditions had high inclination. That was my point, you know, it's just, wow, look, what you get all these. The reason is the outer bodies just have all the angular momentum, and they can do what they like to the little one on the inside, so you can just have any, it could be at any inclination for almost the same initial conditions. So, I don't know, I mean, if these retrograde orbits hold up, I don't know how else you could get them with that, but, you know, Cos-I is always induced for funny inclinations, but I really can't see how that can work with this. Anyway, something new and different. Okay. Oh. Who's taking it? Okay. Any more questions? Oh.